Ну что? Тест, тест. Ну, проверка, проверка. Okay, sorry, the exam is not checked yet, but I promise to do it next time, before the next lecture. So just a small remark about homework. Okay, problem one was fine, more or less, in almost all students. I think those who understood how to do a similar problem with two open sets in a covering, then they did this one. Okay, the second one, yeah, almost also many students solved it. Yeah, so common mistake here. Common mistake was that people chose a covering whose open sets are not simply connected. Yeah, so for example, okay, so for example, some chose a covering something like that. I think one open set was like this. So this is U1. Yeah. The other open set was like this. Yeah, and okay, maybe I don't draw precisely, but I think everybody understands the idea. Yeah, so but the U1 and U3 are not simply connected. Yeah, so not simply connected. Yes, yes, because yeah, these two things they glue. So this U1 is a cylinder. Yeah. Yeah, so not simply connected. Yes. Okay. Yeah, and okay, this was a common mistake. So, and several people chose other covering, also with not simply connected, non-simply connected sets. And then about solution. Okay, standard solution. Choose a covering with 3 sets. With 3 sets. Yeah, for example. Yeah, for example. Okay. There are many ways. For example, like this. This is U1. U2, and for example, this one. Yeah, because I mean these sides glue, then this is actually a disk. Yeah, so all these open sets are actually disks. Yeah, so this is U3. Yeah, this. Okay, I mean, okay, this is okay. You can glue it. Okay, you glue this one. Yeah, 2, 2. So you just move this thing here. Okay, and then 3, 3, 4, 4. Okay. You can see how you glue. You glue these two guys. So So this goes up, and then you glue. This is 1, okay, and this is 4, 3, and you do here the same. You move this piece up and this down. 4, 3, and then you glue. Yeah. So you interchange these two pieces, and then you get a disc. Yeah. Yeah, standard game that students here play on the first course, on the topology course. Okay. Yes, and use problem 1. But actually, there is a nicer solution. There is a better solution. Better solution, I mean shorter. Because here, yeah, one, of course, there are some computations, but actually better solution, there is a covering with 2 open sets. There is a covering with 2 sets. And this goes as follows. So this, okay, this topological space is a Tor without a disk. And yeah, again, from the first year course on topology, we know that Tor without a disk is a square with 2 ribbons. Yeah. So this actually thing where we glue is actually homeomorphic to you consider a square, and then you glue 2 ribbons. Yeah, so you yeah, I guess like this. Yeah, so and yeah, I'm not good in drawing these things. Yeah, why do I draw it like this? Yeah, it should go here. Yeah? Okay, okay, and then you another one goes like this. Yes. Yeah. Okay, I need a good drawing, otherwise it's not clear. No, you see, we glue 2 ribbons. So this is yeah. So it's not closed. Yeah. So it's actually torus with the hole. The hole, where is the hole? This thing that this disk that we cut out is this one. Its boundary is this one. So ribbon lenta. You see that the boundary of this of this object is a disk. It's actually the disk that we cut out. Yes, yeah, and then yeah, then we can cover it with 2 sets. Yeah, one is yeah, you choose yeah, this, and okay, so you something like this. and another one is yeah, is this one. So you green one you yes. So you this and and you go here. Yeah, I hope you understand, yeah, how it works. Yeah, so yeah, and these are intersections. Yeah, okay, maybe I can. So yeah, these are intersections. This one, and this one. Intersections. Yeah, so this is U1. Yes. Yeah. And then we use just our previous result about the computation of Chromology with the covering with two open sets. Okay, so there is this nice solution. Very good, actually. Yeah, my idea was to do this one, so I like this one. Okay. Okay, then are there any questions? Okay. If no, then we continue. Okay, we continue to study Coconology groups. So last time we proved the following result. So X topological space, F sheaf of abelian groups, U covering, and actually two coverings. So we have V coverings, and then we proved that then this map, restriction map, TUB, from the Coconology with respect to covering U is injective. Yes. Yeah, and then so we proved it last time. Then the corollary. The corollary is the following. Again, under the same assumptions, we have we have the map from the Coconology group with respect to a covering to the Coconology group of the space. Yeah, we denote it by TU from H1 UF to H1 XF is injective. Is injective, and the second that if H1 X F equals 0, then this implies that H1 UF equals 0. Okay, obviously the second one follows from the first one. Okay, yeah, and then it's easy. Easily follows from this previous result. So what we do, so suppose T U alpha is equal to 0 for some alpha yeah, then yeah, by definition of the cohomology groups of our space, then by definition there exists an open covering beta finer than U, such that TU yeah, and then by the previous result we get that alpha is equal to 0. Yes, yeah, and then yeah, 2 follows from 1. Yes. So in particular, okay, for example, yeah, those people who okay, if you do you compute cohomology, for example, here, if you compute cohomology with respect to a covering that is not simply connected, then this gives a partial information, yeah, because then if you compute such a cohomology, then you see that the whole cohomology is bigger than what you compute, yeah, because this map is injective. Yeah. So if you compute cohomology with respect to some covering, then you know for sure that the whole cohomology is bigger. Okay. So in principle you get something. Are there any questions? Okay. If no, then we continue. Then actually let us prove this result that we always used. That if the cohomology groups of the elements of the coverings vanish, then the cohomology of the covering is equal to the cohomology of the space. We used it many times. Again, the same as general assumptions. Suppose H1 UI F is equal to 0 for any then yeah, then the cohomology of the of this sheaf is equal to the cohomology with respect to this covering. Yeah. Okay. And the proof is the following. Suppose we have a covering, an open covering beta. So we have, yeah, again, let us fix some notation. So we have a covering UI by UIs. Then we have a covering beta consisting of open sets V alpha. Okay, A. And suppose it is finer than U. No, I say suppose. Yeah, suppose we have some finer covering. Let us prove that. I want to prove some technical statement. Let us prove that the map TU beta from H1 is an isomorphism. Is an we already know that it's injective, so we only have that we only have to prove that it's surjective. So enough to prove that it is surjective. Surjective. Okay. Yeah. So we choose. This is a similar game that we played last time with this statement. So we choose some co-cycle with respect to the covering beta, denoted by F. It's a co-cycle with respect to the covering beta. Yeah, and we have to construct a co-cycle here that maps yeah, to a co-cycle that is whose difference with this one belongs to the co-boundary. Yes. So what we do? Yes. Okay. Again, we have this is a finer covering, so we should fix a refining map. So we fix a refining map from A phi from A to I, yeah, meaning that V alpha, yeah, is inside U. Yes. Yeah. So we have so UI. If we intersected UI with V alpha, alpha in A. So this gives an open covering of UI, yeah, denoted by UI. Yes. Okay. And by this corollary, so since we know that H1 of this covering UI is equal to 0. Yeah, because we know that the cohomology of UI is 0. But then by this result we know that cohomology of any open covering is 0. Yes. Yes. And then we can choose, we can consider this f alpha beta. Ну вот же результат, смотрите, видите? Если у нас к гомологии всего пространства равно нулю, вот написано же, да? Вот, где там это? Вторая часть. Сейчас теорема. Вот же, да. То есть, если h1 равно нулю, значит, когомология любого открытого покрытия равно нулю. Вот. И это мы здесь пользуемся этим. Then we say that f alpha beta will restricted to ui, v alpha, v beta. Yes, so this family is an element of the so is a cocycle with respect to this covering. Yeah, because you consider pairwise fix I and consider pairwise intersections here of these open sets. So okay, so this is so and then we know that since the Chromology is 0, then we know that this is coincides with B1. So there yes, so there exist GI. So there exist sections of our sheaf over these sets. Okay, that give an element of that give a zero cochain of this open covering, such that the boundary of it is equal to this guy. So, okay, it means that there exist elements GI alpha, F UI, such that f alpha beta is equal to GE. GI, yes, GI beta minus GI alpha on UI okay. Yeah, then yes. So we have this equation. Yes. Then we consider open covering. So now we consider such intersections UI, UJ, V alpha, alpha, A. This is open covering of UI, UI intersected with UJ. Yeah, and then on UI intersected UJ, intersected V alpha, intersected V beta, we have what we have. Yeah, we have so that F alpha beta is equal to this thing, GI beta minus GI alpha But since we take the intersection with uj, we have the same equality for j. Gj beta minus g j alpha. So so this so we just rearrange it and write it as g j alpha minus gi alpha is equal to g beta minus g I beta. Yes. Yes. So you and then you apply Schiff axiom to the covering to the covering of this intersection by the sets you yeah, but by these sets, yeah, UI.
So you can have, can I ask you a question? I don't really get what's going on. Where you write this f alpha beta is restricted to belongs to the one cocycles. So first things first, I guess it's phi alpha phi beta because alpha and beta are indices both for the covering V and the covering U.
No, alpha beta are from this index set that indexes the covering B. So V alpha. Yeah, and okay, okay. So what is not clear? Во-первых, вопрос как бы в чем? UI, здесь бета обозначение для этого открытого покрытия, для этого семейства открытых множеств. Ну а что такое покрытие? Покрытие — это множество открытых множеств, ну, объединение которых... Да, ну, fix, yes. So, yeah, this is open, okay, I did not write it. So this is open covering of UI. Yeah.
So F initially is a collection of intersections of sections of intersection of F over UI intersected with J, right?
No, of V alpha with respect to V beta. So now we want to construct an element here. Yeah. Yeah. So actually we're already here. We're already at this point because we want to construct something over the intersections UI. We want to prove that there is an element here that goes to this element. So we have to construct some cocycle here. Yeah. So we have to construct sections over UI intersect with UG. Yeah. And okay, so okay, we found some element gi alpha, and then you see, we consider these intersections UI intersect with UJ, and then we consider an open covering of it, and consider these elements. Yeah, so these elements J. So we know that Gj alpha minus G alpha, they are sections over UI, UJ V alpha. Yes. And then this relation says that on the intersections, on pairwise intersections of these sets, these sections agree. Yeah. So we can apply Schiff axiom 2 and we can apply and find some sections Fij section of our sheaf over Ui intersect with Uj such that Fij restricted to Ui Uj V alpha is equal to J alpha minus Ji alpha. Yes. Yes. Okay. Okay. So we constructed some element. Fij is an element. Is a okay. At the moment we know that it's cochain with respect to the covering U. Okay. Then now we have to check that it's a cocycle. So let us check. Let us that Fij belongs to so it's a cocycle actually. We can denote it F. Okay. Yeah, and so we check. So we write delta F ijk is equal to, okay, just by definition, F jk minus Fi k plus Fij. Fij. Yes. So we want to check it on, of course, U alpha, Ui, Uj, Uk. But let us check it on the intersection with V alpha. Yeah, then we can apply these formulas. Yes. You see that Fij on this intersection is Jg alpha minus Ji alpha. Yeah? So then this is equal to J k alpha minus J G alpha minus J k alpha minus Ji alpha plus yeah, actually by construction on this restriction, yeah, it's 0. J alpha minus yes, and this is 0. Yeah, so here we use this formula, this one. So if we denote it by star. Yeah, so this is 0. So you see that delta F ijk restricted to ui, uj, uk for any alpha, then by sheaf axiom 1, sheaf axiom 1, so you see that delta f ijk is equal to 0. So indeed f is a cocycle. Okay, and then we yes. Yes, and so finally then we write, then finally on V alpha intersected with V beta, what we have? F phi alpha plus phi f phi alpha phi beta plus f alpha beta is equal to so now we have to use several what we have. Yes, so we have to use first of all this formula star. So this is, you see, phi alpha, phi beta. So here you get u phi alpha, u phi beta. But u phi alpha contains v alpha. Yeah. So and u phi beta contains phi beta. So actually this set contains v alpha, v beta. So we can apply this formula. We apply this formula. So this is G. Yeah, okay. So we apply this formula. This is phi alpha, phi beta. So J yeah, phi beta. So this is G phi beta alpha minus G phi alpha alpha alpha, and I apply this star plus f alpha beta, and then we continue. And we yes, we also had this formula. Okay, we can denote it by 2 stars. Here I is phi alpha. We take I equals phi alpha equals G phi beta alpha minus G phi alpha alpha plus f alpha beta. I is equal to phi alpha. No, phi beta. Yes, I should be equal to phi beta. Yes, we should take I is equal to phi beta in this formula. Then you get here G phi beta beta minus G phi beta alpha. alpha. And then these two guys cancel. And then you get that G phi beta minus G phi alpha alpha. Yes, and then okay, and then you just denote let H alpha consider a zero co-chain with respect to the covering beta, where H alpha is by definition this thing G phi beta restricted V alpha restricted to V alpha. Yes, and then this formula says that then so what we get? We get that yeah, so we get that this co-cycle F alpha beta by this formula it is equal to the restriction of this co-cycle, and using our notation it means that minus F plus co-boundary plus delta H. Yes. Yeah. F F star F sharp is a map from yeah, okay, ZQ UF to ZQ UF such that ZQ beta F. So if you have here some element F I0 IQ, then phi of phi sharp F alpha 0 alpha Q, just restrictions. So you take just restrictions. F phi alpha 0 phi alpha Q restricted to these intersections V alpha 0. Yeah, I mean, okay, formally speaking, yeah, of course we define it for co-boundaries, for co-chains, but yeah, it maps co-boundaries to co-boundaries and co-cycles to co-cycles. Yeah. Okay. Yes. Yeah. So this proves what we want. Yeah. So this proves that. So this proves that this map Tu beta from H1 U F to H1 beta is an isomorphism. Yes. Yeah, and then we have to. So we proved this statement. this one. But then we want to prove this. I mean the theorem. But then it's easy. So let us now prove that this map TU from H1 UF to the Coconology is an isomorphism. Again, we know that it's injective, so we only have to prove that it's surjective. Only have to prove that it is surjective. Yeah, so what we do, we just yeah, so we choose alpha in this Coconology. Then let alpha prime in H1 U prime F be a representative of alpha. Representative of alpha. Then we consider Coconology classes are represented. Coconology classes from this space, from this group, are represented by Coconology class with respect to some coverings. So we take a representative. A representative is a Coconology class with respect to some covering. So U prime is just some covering. Yeah. So then we consider the covering consisted of intersections. Yeah. So U prime is some covering. U J prime. J is in J. Then we consider the covering beta, again, which is finer than both U and U prime. So it consists of intersections UI, UJ prime. Then ну как, ну мы хотим доказать, что это отображение сюррективно, да? Ну то есть, ну вот мы по определению доказываем, что мы давайте найдем, то есть для любого элемента здесь есть элемент здесь, который в него перейдет, правильно? Ну, потому что как мы определяли вот эти когомологии? Это класс эквивалентности, это элементы здесь, это класс эквивалентности когомологических классов по отношению к произвольным открытым покрытиям. Вот. То есть мы вот и действуем по определению, выбираем какой-то вот класс когомологий, представитель, да, ну вот по определению он должен быть, да, принадлежать каким-то когомологиям по отношению к какому-то открытому покрытию. Okay, then we consider the pair of intersections. Then, but then there exists gamma in H1 U. You see that U and U prime, so beta is finer than both U and U prime. Then there exists gamma such that tu beta gamma is equal to tu prime beta alpha prime. Yes, because so we with tu prime beta alpha prime, it is a Chromology class with respect to this covering, but then we proved that the map from here to here is surjective. So we know that there exists such gamma such that the element here is the image of the element here. Okay, but then by definition this element is equivalent to alpha prime. Okay, so by definition tu of a gamma is equal to alpha. Yes. So just a formal application of what we proved. Yes. Okay, are there any questions? Okay. If not, then we continue. So basically, so this is by definition, so this is equivalent to gamma. So gamma is equivalent to alpha prime. So this means that this map is just takes the equivalence class of gamma. So if gamma is equivalent to alpha, then is equivalent to the representative of alpha, then okay, this is what we want. Okay. So okay, then we finish general theory of shifts. Then we go back to Riemann surfaces. What is a goal? Big goal is to prove the so-called finiteness theorem that H1 of XO is a finite dimensional, dimensional vector space, and then the genius of X is actually defined as the dimension of this space. Is a finite dimensional vector space for compact Riemann surface. For compact Riemann surface X. Then the genius of X is the dimension of this space. Huh? It's rot. Yes. And then we will actually, this coincides with the topological genius. This we will discuss. Okay. But this is a goal, so I think it will take several lectures to prove this finiteness theorem. It's not easy. Okay. And then the first step is just to put, as usual, I mean, in order to compute cohomology. Yes, yes, of the structure sheaf, yes. Yeah. For compact Riemann surface X. And as usual, so we know, yeah, we like to compute cohomology groups using. Да, это и есть, да, гламурная функция, да. Yes, so we like to compute cohomology using coverings such that this property is satisfied. Yeah. So okay. So we want to use this theorem, but then we have to we have to prove that that H1 of some sets of the sheaf O is 0. Yeah. In order, if you want to use this theorem. So in the first step, so step 1, is to prove that H1 of a disk of an open set, or I think we used the notation BR, O is 0. Where I recall that BR is the set of complex numbers such that the absolute value is less than R. And then okay, also here R is greater than 0 and less or equal than infinity. Yeah, so formally I would like to allow, so B infinity is just the whole C. Okay, this you want to prove. Okay, and then the first statement here is the following lemma. So this is just a plan. But then how we what are the statements that we now want to prove? There's the following statement. Suppose yeah, sorry, probably yeah, okay, I guess let's just show a short reminder that that if we have some open set U in C, yeah, and then if you open set, then you have some function f, smooth function, then we have the operator f dz, which is equal to 1/2 d dx minus I d dy of f. Yeah, and then we have an operator dz bar. Plus I d dy f. Yes. Yeah, and then okay. F is a holomorphic function if and only if df dz bar is equal to 0. Okay. Okay. Here, suppose we have some function g, a smooth function on C with compact support. Compact support. Then there exists a function f smooth function on C such that df dz bar is equal to G. So we can solve this equation. There is an explicit formula for f. So we define so we want to solve this equation. So we define f of zeta by the following explicit formula: minus 1 over pi integral over R2 G z minus zeta dx dy. Yes. Okay, yeah, first of all we have to justify that this is well defined. So let us prove that f is actually a smooth function. Is a smooth function on C. Yes. Yeah, okay, the standard thing that we make a change of variables. We go to polar coordinates. Change of variables. So we write that z. Okay, z is of course x plus iy. So we write that z is equal to zeta plus r e to the power I phi. Yes, and then okay, we do this change of variables. Then f of zeta is equal to minus 1 over pi integral. So we integrate r from 0 to infinity, and theta between 0 and 2 pi. And then we write here g of zeta plus r divided by r e. And then we know that the Jacobian of the this change of variables to polar coordinates is equal to r. Yeah, so times r dr d phi. Yes. Yes. So sorry, phi. Yes. Yes, it is a misprint. This angle phi. Yeah. So yeah, every we have phi. Yes. Okay. So we see that r disappears. Integral g zeta plus r phi. Yeah, e to the power minus I phi dr. Yeah, so you see that singularity disappears, and also also this integral is finite, yeah, because we know that G has compact support. So actually here, yeah, you can just integrate over some finite set, a bounded set. So actually this integral is well defined. So here you use that G has compact support. Has compact support. Okay, maybe I just write it. So since G has compact support, then you can actually integrate over some set is less or equal than R and phi 0 is equal to 2 pi. Yes. Yeah, where R is some big number. Okay, and then if so here you integrate over some rectangular, some smooth function, depending on R and phi. And of course you can differentiate under the sign of the integral. So this implies that indeed f is a smooth function on C. А? Ну как, я же, что здесь? Ну, мы же как, мы хотим, значит, доказать, что, ну, во-первых, что она определена, эта функция, да? То есть мы фиксируем z, да? Вот. И дальше вот записываем в полярных координатах, вот получаем такой интеграл, да? Вот. Ну, вначале мы как бы решили проблему вот особенностей, да? Что особенность исчезла, то есть мы интегрируем, получается, гладкую функцию, да? Ну, а теперь мы хотим обосновать, но все-таки, формально говоря, мы здесь интегрируем ну, по бесконечному множеству. Теперь мы хотим обосновать все-таки, что интеграл-то сходится. Вот. Но дальше мы замечаем, что функция, что вот эта функция, она имеет компактный носитель. То есть получается, у нас z фиксировано, да? То есть если r достаточно большое, да, то эта штука зануляется, правильно? Ну, то есть получается, что если мы выберем достаточно большой r, да, то вот эта функция будет зануляться, ну, вне этого, да, ну, при фиксированном z. Вот. То есть, да, при фиксированном z она определена, получается, корректно. Вот. Ну и понятно, да, что если дальше мы хотим доказать, что она гладкая, да, то есть получается, ну, мы говорим, что z, она там в окрестности, маленькой окрестности какой-то точки. Ну и опять же, мы можем выбрать большое какое-то r, что эта формула верна для всех z из какой-то маленькой окрестности фиксированной точки. Okay, so this computation proves that f is a smooth function on C. Yes. Yeah. So, okay. Then let us prove. Okay, I think we can do it. Okay, let us prove that df d zeta bar is equal to yeah, g of zeta. Okay, so we integrate df d zeta bar. So we just differentiate under the sign of the integral. So we write minus 1 over pi integral d g plus r e d zeta bar e minus I phi dr d phi. Yeah, then in order to compute it, we we make again back the change of variables. So yeah, okay, yeah, formally, so yeah, we write this integral, but then let us formally, because we will now make the change of variables and again some singularity appears, so we write that this is equal to df d zeta, and then we can, and then here choose epsilon, and say that this is the limit epsilon goes to 0 of this expression. Yes, and then we make back the change of variables. We say that r e I phi is equal to z. And then we obtain that this is equal to minus 1 over pi no, this is correct. Yeah, we want to change this to z. Yeah. Yes, and then we integral. Yeah, and here we lesser or equal than r. dg zeta plus z d zeta bar 1 over z 1 over z dx dy. Yes. Yeah. Yes. Yeah, and then we can what we can do, we can yeah, so we can replace then write that this minus 1 over pi limit epsilon goes to 0. We can replace here the derivative by zeta by the derivative by z. Yeah, so integral d g zeta plus z dz bar 1 over z dx dy. And then we actually, yeah, we know that 1 over z is a holomorphic function, so this is minus 1 over pi. Чего? Вот этого? Сейчас, ну смотрите, ну у вас функция зависит от ну, двух переменных, ну от суммы переменных, поэтому ну, производная по одной переменной, она ну, равна производной по другой. Правильно? Ну, как, если у вас есть функция там ну, f от x плюс y, да, то производная по x, она равна производной по y. Правильно? Ну, это как бы следует из этого формулы там, замены переменной или как там дифференцирование композиции. Okay, so limit. And then you move d over dz bar. And here you write g of zeta plus z over z dx dy. Yes, and then what you write? Okay, and then you want to apply Stokes theorem. Yes, what you say? You say that note that. Okay, then probably we have to make a break. Yeah. Well, okay, let us make a break and then we will finish it. ладно. Хорошо. Okay, so let us finish this proof. Yes, so just again here maybe I write remind some standard thing from theory of complex functions. So again we have so if you have some function h, some smooth function, so u some open set, then yeah, I recall this operators d over dz and d over dz bar. Then we also have differentials, yeah. So of course dh is equal to dh dx dx dy, but yeah, so if z is so z is I, so dz is dx plus I dy, dz bar dx minus I dy. So, and then elementary computation shows that yeah, I hope everybody did in the course of complex analysis, that this is equal to this thing, dz bar dz bar. Yes. So, and then we can also compute how to compute dz wedge dz bar. This is equal to minus 2i dx dy. Yeah, so yeah, so we use that. So we say that, yeah, we replace it by wedge, and then I write that this is equal to minus 1 over 2i dz bar. So this is equal to minus 1 over 2 pi I limit integral. Here we have dz bar, but here yes, yeah, okay. Maybe I write minus, and then here I write dz bar dz, and then here we can write the differential of this thing, g of zeta plus z over z. Yes, because the no, sorry, wedge dz. Yeah. Why? Because if you write the differential, then you get d over dz bar, then it gives dz bar dz, and it gives what you want, but then it also gives d over dz, but dz wedge dz is 0, so okay, so we have this formula. Yeah. So we can apply Stokes formula. So again, here we should remember that we integrate, and then this is equal to 1 over 2 pi I. Вот здесь вот? Ну, ну, смотрите, вот здесь же у нас берется dz с чертой, правильно? Поэтому, если берет дифференциал от этого, здесь вылезает dz и dz с чертой. Но dz, он убьется с этим, а dz с чертой как раз даст производную от этого по dz с чертой, ну, и вот эту форму. Да. Ну, я туда-сюда минус написал просто, и все. Ну, смотрите, здесь да, здесь был dz с чертой минус 1 делить на 2i. И здесь минус. Они дадут плюс. А дальше я хочу их поменять местами, опять дадут минус. Вот. Okay, we apply Stokes' theorem. So Stokes. And then, okay, so what is our domain? So our domain is such as thing. So this is R epsilon, but our function is 0 here. So I mean R is big enough, so our function is 0 on this boundary. So so we should so we integrate over this circle, over this. Let us denote it by, I don't know, C epsilon. Yeah, integrate over C epsilon. What I want to say? Sorry, I mean this is of course then. Sorry, this is dz, and then like this, of course. Yeah, so it gives what we want over C epsilon of this form d g of zeta plus z over z dz. А? Ну мы же выбрали R, у нас функция обладает компактным носителем. Что это штука? Мы выбрали такую большую R, что вот, ну, это равно нулю на границе внешней. Да? Okay, so and then again we go to polar coordinates. So z r I phi and and then we get integral 1 over 2 pi integral over the average over this circle. Yes. Yes. Integral over 2 pi. Integral 0 to pi g of zeta plus epsilon e I phi d phi. Yes. Yeah. So, but this we here everybody we have limit. Yes, here we should take limit, and here also we should. So z equals r equals limit. But then, okay, here what you do, you take your function, and then you take the average of your function around this point. And then you take the limit, epsilon go to 0. So your function is continuous, so this is equal to g of zeta. Yes, so this proves this statement. Are there any questions? Okay. Yeah, so we proved that if G has compact support, then we can solve this equation. Well, actually, next time we will prove that this is true for any smooth function, not necessarily with compact support. And then from this, we will this statement will be an easy corollary. Okay. If there are no questions, then we let us probably maybe do some exercises. But for that, let us introduce some new sheaves. Actually, we will need them. Yeah, so let us consider the following definition. Suppose we have some Riemann surface. X is a Riemann surface, and we have some holomorphic, some differential form omega. Then we say that omega. So we say that omega is of type 1, 0 if in any coordinate chart it has the form omega is equal to some function omega dz, where f is smooth. So yeah, okay, and then respectively 0, 1, respectively of type 0, 1. Yeah. If in any coordinate chart it has this form, and respectively f dz bar. Yeah. So we know that any form omega can be written as f dz plus g dz bar. Yeah. If we consider a form on a complex plane, then we can write it in this way. Yeah, of course. But then we say that it is of type 1, 0 if it has this form, or 0, 1 it is of this form. But then, of course, we have to prove that it's well defined, that the definition is correct. Yeah, because I mean, meaning that we say that in any coordinate chart, it should have this form. But okay, suppose, we should check that if we consider another chart that is intersected with this chart, then it is again v of this form. Yeah. So let us check. So suppose you have a chart. Suppose we have charts okay, some u. Recall that our charts are functions, yeah, from u to c. We have charts u and okay, some z tilde from v to c. Yeah, so these are subsets in our Riemann surface. Then if omega is equal to f dz on u, then on the intersection we have what we have. We have that f omega is equal to f dz. But yeah, strictly speaking, it is equal to f dz over dz tilde plus dz tilde bar dz tilde bar. But then our maps are holomorphic. So z, I mean, this is a holomorphic function of z. So this is 0. Yeah. So so it means that our definition does not give any contradiction. Yeah. So if in some coordinate chart a form is of type 1, 0, then in any other coordinate chart it is also of type 1, 0. Yeah. And then is it clear what I said? Okay. Yes, and then define epsilon 1, 0 of u. Define let it be the space of of forms omega omega is of type 1, 0. Yeah, so consider the following subspace in the space of all smooth forms. So U is an open subset of our Riemann surface. So we would like to consider now forms of type 1, 0. And similarly 0, 1. Okay, and then we also would like to consider holomorphic forms. So if U is a subset of our Riemann surface, open subset, then omega a holomorphic form of type 1, 0 is called holomorphic. It's called holomorphic. If in any coordinate chart it has the form omega is equal to f dz, where f is holomorphic. Where f is holomorphic. Yeah, and then the notation is that omega u so it's the space of holomorphic forms. Yeah. So what we have? So what we get? We get that we have the space of smooth one forms on U. Then inside we defined the space of smooth one forms of type 1, 0, and then inside define the space of holomorphic one forms. Yeah. Okay. And then here we also have forms of type 0, 1. Yeah, and then all these guys form sheaves. So omega are sheaves. Sheaves on X. Is it clear? These are important sheaves. We will use them later. So this is sheaf of smooth one forms of type 1, 0, holomorphic one forms. Okay. Okay, and then the problem. So this is an exercise class. So let us try to solve something. Let us compute the space of holomorphic one forms on the sphere. So problem 1, exercise 1, compute omega of CP1. Okay, yes, then how to prove it? Sorry?
I guess you can try actually.
Okay.
You should do the same as break for hands.
S2? Нет, видите, здесь же важно, вот когда мы определяли понятие формы типа 1,0, да, ну, как бы это все корректно определено, только если функции перехода голоморфны, да, то есть, ну, как бы надо все-таки говорить про CP1. Ну да, то есть только на комплексное многообразие определены вот эти разложения.
As usual, we use the homogeneous coordinates z0, z1. Yeah.
To be honest, we didn't discuss them. Okay, but if you want, okay, I guess everybody understands that. Yeah, okay.
Well, the usual coordinates.
Yeah, I understand. Yeah, but I mean, we just introduced CP1. I mean, using just two open sets. Yeah, but okay, it is not important. Okay.
Okay, and we have the corresponding affine charts. What I'm to prove is this is just there is only one such form and it is being zero.
Mm-hmm.
So this is like the zeroth vector space.
Yeah.
And I'm taking any differential any homomorphic form. And I will show that. I hope I will show that it is zero.
Mm-hmm.
Okay. Now I introduce the usual homogeneous coordinates on CP1. And then I see that Y are affine charts. Then omega are restricted to, say, U0 should be f of z1, dz1, right? Well, U0 is where the z0 is non-zero. Sorry, the pun. And hence we have the local coordinate z1. And due to our definitions, we see that they are using representation of this form, right?
Mm-hmm.
show that, well, in fact, we will have to show that f is equal to 0, because if f is equal to 0 everywhere on u0, then f being continuous must be also equal to 0 on the left point. That is not covered by u1, right?
Yeah.
So yeah, and then changing coordinates, we get
What is it do?
yeah, no, it's z1, z0, there should be. So z1 is 1 over z0, right?
Yeah.
Let's see if I have a prediction or I will not.
Yeah. Yeah, I mean, I just write in our, in our notations, because we didn't speak about homogeneous coordinates. So formally, how we I say just the same what you want, but so we covered CP1 by 2 charts, yeah, and then there is function you want it to be denoted Z1, yeah, to C, and here we have coordinate chart. So coordinate charts. Coordinate charts. Yeah, so we have two coordinate charts, U0 and U1, and then on indeed U0, which is equal to C star. Yeah, we have Z1 equals 1 over Z0. Okay.
Okay, yeah, I guess it works. Now, there should be a removable singularity at 0 for this function, right? Because, because it's actually a restriction of some homomorphic function that we could get from U0, U0. I guess I should call it U0. Okay.
So no. No, you should replace here Z1 by 1 over Z0. Yeah, because the Z1 is Z0. Yeah?
That's true. I guess it shouldn't mess anything up. Well, yeah, it doesn't change anything. Which, in particular, да, не должна это сделать, это будет парноголоморфно. So which in particular, I guess should be enough for me, implies that the limit as z1 tends to infinity of f of z1 is 0, right? At least it's true.
Yes, so what you say. Yeah, so this form should be, so this is a holomorphic form. Yeah, so you go to another chart, then this should be a holomorphic function. So in particular, when you z0 goes to 0, you should have a limit. Yeah, this guy.
Yeah.
But then it means that, okay, at least it means that this numerator should go to 0 when z0 goes to 0. So this means that when z1 goes to infinity, then this guy should go to 0. Okay.
And then
Yeah.
I believe by Liouville's theorem we are done, actually.
Yeah.
But
Yeah.
f is everywhere equal to 0.
Yeah. So indeed, yeah, he gets that f is bounded, so f must be a constant. But then, since the limit at infinity is 0, so this constant is 0. Yeah. Yeah. Okay. Yes. Okay. So. Ну, если предел на бесконечности равен нулю, правильно? Okay. Are there any questions? No. Okay. Okay. Actually, it's these computations can be yeah, actually useful for one of the exam problems actually. Yeah. So for this, I would like to suggest to compute now the space of holomorphic one forms on the torus. So compute omega of a complex torus.
If we believe that our goal is true, then it should be equal to C, right?
Okay, yeah. So prove that. Yes. Какой теоремы? Ну, не, ну мы хотим все-таки же это... Ну, та теорема сложная, тем более она как бы и тоже из нее не вытекает. Он же первой когмологии пучка, структурного пучка. А чтобы получить этот факт, надо еще двойственность сервера применить, да. Короче, мы это не хотим пользоваться. Нет, это же I suggest it is possible to obtain it by direct computation. So let's see. Quotient by gamma. Yeah, actually, yeah. So, yeah, actually, yeah, if we want to prove that this is C, so we should at least show that there is some non-zero holomorphic form, yeah? So here we had to prove that for CV1 we had to prove that every form holomorphic form is zero. Here we have non-trivial holomorphic forms, so we should at least show at least one example. Yeah. Нет, зачем? Нет, при чем тут нет здесь? Я как раз наоборот хотел, если решить это, то с помощью нее можно как бы, ну, например, доказать задачку из экзамена. Вот. Потому что, yeah, so, yeah, I wanted to show that if we prove this, then it gives a nice proof of the exam problem, of one of the exam problems, because if there is a holomorphic, because if there is a non-constant map from CP1 to, so if this is true, suppose this is true, then if there is a non-constant holomorphic map from CP1 to a torus, then you can choose a non-zero holomorphic form on the torus. Yeah, yeah.
How should I do this correctly? Okay, is it clear that disease is well defined on the Riemann surface on the complex torus?
Yeah,
It is because, well, we have local isomorphism, which gives us dz locally, and when we need to show that they grew up correctly, and well, they do. Well, yeah, that's basically the speculation.
yes. Yeah, okay, so you want to say that, yeah, indeed. Ну, сейчас, давайте закончим это тогда, да. Да, да, okay. So you want to say that dz, so claim dz is well defined on on our complex torus. So, but how to justify that formally? Yeah, okay, okay. Yeah,
take any point, and we want to define a block near this point, make a small neighborhood of it,
yeah.
then have trivial covering over its VC.
And
so we can then pull back dz from any of the neighborhoods in the open covering.
Yeah.
Though all the pullbacks are the same.
Yeah.
Therefore, doesn't matter from which neighborhood we pull back the form.
Yeah.
They're all the same.
And
that's it basically, because now we just take the neighborhood of each point, pull back the form, and we need to check that they agree on intersections.
Yeah.
Intersections have the very same picture.
Yeah.
So they must agree, and that's it. And
Yeah.
that's actually proves everything, because so this is.
Yeah. Okay. Let us maybe write something for this. So why it is well defined. Yeah, indeed. How? Okay. Yeah, more or less the same what you said. That I mean, we said that if X is a Riemann surface, we said that omega one form. So if we have some one form, then omega, it means that at each point, so omega at each point X in our Riemann surface is an element in the tangent space, yeah, in the cotangent space of X. Okay, complexified. Okay, so we need to check that yes, so yeah, so but how to say that? yeah, the tangent spaces are all identified. Yeah, so all yeah, so I mean we have the map pi, the projection from from C to our torus. So and then all the tangent spaces here. I mean we have the isomorphic to each other, and this gives an isomorphism of all the tangent spaces here. We just fixed vector space, yeah, and then we just define its section by dz. Okay, I mean, okay, maybe it's not better than what you said, but okay. Does anybody believe in this, that dz defines holomorphic one form on a torus? Yeah, yeah, yeah. Yeah, I mean, maybe one can say the following. So how we define coordinate charts on our torus? Yeah, so coordinate charts on X quotient gamma. So we said that we have this projection from C to C, and then we choose here U such that P of U is an isomorphism. And then we said that then the map, then P inverse from PU to U is a coordinate chart. Coordinate chart, and then okay, and then and this is how we define the complex structure on our torus. And then if we, and then his argument is that if we consider another coordinate chart, then the transition function between these two charts is just shift. Yeah, so so if we have another coordinate chart, then transition function is just yeah, so one coordinate is another one plus some constant. So if we have one form dz in one coordinate chart, then okay, it doesn't change. Yeah. Yes, yes. Then how to prove that there are no more?
It's compact, therefore all the functions on each are constants.
But how do you go from holomorphic one forms to?
Well, you see that evidently C lies.
Yeah.
So now take any holomorphic one form on the torus.
Yes.
It is of the form f of C times dz, right?
Yes.
Well, then you get a holomorphic function from the torus, which is compact.
Mm-hmm.
Hence, the function must be constant, meaning the form is of the form, again sorry with pi, a scalar times dz.
Yeah. 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 So he says that since dz is not 0, at any point of C gamma, any omega, any holomorphic form on our torus has the form omega equals f dz, where f is a holomorphic function on our torus. And then, since I mean the torus is compact, then f must be constant. So any holomorphic one form is a multiple of this dz. Yeah, is it so? Контрольные. Да, ну вы готовы это показать? Можете показать это?
Ну, я некоторое время подумал, как ты вопросы, скорее всего, не получится.
Ага. Yes, indeed. Yeah. Yeah, so it can be used to prove that there are no prove that there are no non-constant holomorphic maps from CP1 to the torus. There are no. Okay, yeah. Okay, and indeed, yeah, the idea is that suppose there is a holomorphic map non-constant. Non-constant. Okay, and then okay, then the idea is indeed to take this form, holomorphic form. Maybe we can just say that. And then what then?
I want to show that it is equal to 0, right?
What is 0? This form. Okay, you take one form, yeah.
Yeah, and I would like to take its pullback to the projective line.
Yeah, okay. Yeah, we know that we can take pullbacks of forms.
Now I need to show that it is in fact holomorphic.
But okay. That's me. Sorry.
It's clear that it is equal to 0, right?
Yeah, of course. Since it's a holomorphic form, so the pullback is a holomorphic form, so it should be 0. Yeah.
So now assume that since the initial form is on 0, and there is a point, and tangent vector is at the point at which the form is on 0.
Yeah.
So let's take this point in this vector.
Mm-hmm.
As also we know if it's non-constant, since the projective line is compact, the map is.
Maybe you can go and then write something.
implies that phi is surjective. I guess I should rewrite what I've said for this.
Mm-hmm.
So in omega is on 0, omega is on 0, therefore there is point P on the torus and a vector, a tangent vector at this point.
Mm-hmm.
Yeah, it's vector 3. Это лекция 3. Просто много ссылался в контрольных ссылку. Okay, so then let you from
Yeah, actually, I mean, of course, this is true, but we know that the omega is just dz, yeah. So I mean, so at any point, there is this vector, yeah, and any point and any non-zero vector, this is true. Okay, but anyway, yeah.
Well, I guess not any non-zero vector. Should have a kernel, but
Why? I mean, just.
well, it's a full vector, so it has a kernel, right?
Yes, formally it has a kernel. Yeah, okay.
Yeah. So yeah, let Q be a point such that phi Q is P. Well, phi is a covering. In particular, it's local isomorphism. In particular, its differential is everywhere in isomorphism. So phi is a local covering. So the differential phi Q is an ISO. Hence, there is a vector W at the tangent space. I guess I should complexify it maybe. I guess we can do it actually.
Actually, yeah, formally there is a problem here because our form is where is T dual complexified. Yes.
Okay, so that is then.
Okay. Yeah, and this is fine. Okay.
Such that dq phi of W is equal to V.
When you say phi is a holomorphic covering, what do you mean?
Well, phi is a covering, as like topologically, and it's.
No, it's not a covering. Why do you say?
Yes, just want to make sure. It's good to mention. Then, what do we want to show? I guess I will make use of the fact that actually omega is everywhere on 0, because otherwise it might come up badly. So, так дизи просто, да. В смысле. Okay, so we need a point where. Okay. Then make it like let's make it vice versa. So there is a point Q. Well, in fact, there is an open subset of such points, such that okay. Because let's take a point like any point. And we have two cases. Well, and locally, phi is just usual map from a domain in C to domain in C. And we have two cases. Either it's equal to 0 only at this point, or it's locally equal to 0 by the identity theory. Well, if it's locally equal to 0
Mm.
and we get a constant map.
Mm.
Here are 5 such points.
Why? Can you repeat?
Well, okay, assume this is true.
Huh?
Assume it's not
Okay. Okay.
assume the contrary.
Uh.
Then differential is equal to 0 everywhere.
Ah, yeah, of course. Then locally is constant. Yeah, of course. Yeah. Yeah. Mm-hmm.
The projective plane is connected. Okay. There is a vector v in the tangent space of the image of q such that omega v is not equal to 0, right?
Mm-hmm.
Well, since the differential is in 0, it's in fact isomorphism
Mm-hmm.
because it's one-dimensional.
Yeah.
So there must be a vector in tangent space of q such that is mapped to v.
Mm-hmm.
For formal purposes.
No, why formal? I mean, because our one forms are ну, в каждой точке они же, получается, элемент не касательного пространства, а комплексифицированного касательного пространства.
So yeah, and then have the following: omega of v is equal to omega of well, I just substitute what I just obtained, which is by definition of the pullback. You should distinguish these two backgrounds on the left. The 0, which is a prediction.
Yes. Yeah. Okay. Yeah. This is fine. But you could actually well, actually, yeah. Of course, this is fine. But you could also use our result, which makes actually this argument simpler. So what you can say? We can say that actually take any, yeah, so just take any q CP1, then we know that there exist coordinates. So there exist local coordinates z around q and w around phi q such that our map phi of z is equal to z to the power k, yeah, for some k. For some k greater or equal to 1. Yeah, and then yeah, we know that omega, our form omega, is equal to some function f of w dw around phi of q, yeah, in our torus. Yeah, then you can just compute the pullback, and then where phi of 0 is not equal to 0, yeah. Yeah, and then phi star of omega is what? You just substitute f of z to the power k d z to the power k. So it's equal to k z to the power k minus 1 f dz. But this is non-zero around. So this guy, it's not identically 0 around f of around q. Huh? I mean, f doesn't vanish at 0. Yeah, I mean, no, k cannot be equal to 0. I mean, according to our theorem, if we have a non-constant map between Riemann surfaces, then at each point it has this form z to the power k for some yeah, the same, yeah, more, yeah, it's the same, yeah. Ну, мы же выяснили, да, что омега, что наша форма вот эта омега, ну, вот эти, это же там, ну, кратная dz, да, она в каждой точке не нулевая, да. Вот. Ну да, and you see, so f at 0, f is not equal to 0. So this function is not identically 0. Yeah. So this implies that this form, so it's a holomorphic form on the torus, and on CP1, and it's not equal to 0. Yeah, but this is a contradiction. Yeah, because we know that any holomorphic form on CP1 is 0. Yeah. Yeah, actually, this argument shows that, yeah, that there is an injection. Yes, so if you have a map from one compact Riemann surface to another compact Riemann surface, then the inverse map between holomorphic one forms is injective. Yeah. Ну, это другое решение просто. Другое. Ну, не, ну так прям напрямую я не знаю, как сказать это. Okay, maybe yes. Still, if there is indeed this, we discuss this exam problem, then maybe I tell you the solution that, I mean, this solution of exam problem, it uses some material that we didn't study before exam, but so I can tell you the assumed solution for this problem. Не, ну то, что вы, конечно, применяете, это из пушки по воробьям. Вот это про пространство мироморф. То есть применяйте результаты в описании этого, получается, поля мироморфных функций на торе. Да. Ладно. Ну ладно. Assume solution for this problem. А кто это рассказывает? Львовский? Ага. Хорошо. Assume solution for this problem. So, okay, suppose phi in C is holomorphic. Yeah, then what we say? We say that we consider this diagram. Yeah, CP1, C gamma, and then C, this phi, and then from the topology course, we know that this is a covering. This is a covering, and then and we know that CP1 is simply connected. Simply connected. And then, okay, and then there's the standard theorem says that if you fix some point, some q, and then you choose some point here p, such that pi of p is equal to phi of q. So choose. So choose. Then there exists a unique. Okay. Then there exists a unique. Okay. Formally continuous map. Continuous phi tilde from CP1 to C, such that I mean this diagram commutes. So if you apply phi tilde pi is equal to phi and phi, and so we fixed the image of Q. So phi tilde of Q is equal to P. То есть это называется теорема поднятия отображения. Yeah. Then there exists a unique. So this is yeah, this is topology course. Не такая. This is studied at the end of the first year. What you say is studied at the end of the second year. And in not in everybody course, in any course on complex analysis. I mean, this is much more basic fact. Huh? I just say that this is a standard result in topology course. And of course in topology, it is. People study continuous maps. Yeah, but then I want to show that easy check that this map is holomorphic. Check that phi tilde is holomorphic. Yeah, you should just write yes yeah, just the definitions. So then you get it. So basically, yeah, you should write our standard coordinate charts here. So some open set U, and then it's the image of some U here, and then you, yeah. Okay, and then you, okay, see here you choose some small set here that maps inside U. Okay, and then this map is an isomorphism. Okay, I mean, I won't say it's a direct check using our definitions that phi tilde is holomorphic. But then, okay, then you use, but then you, so you get that phi tilde is a bounded. So no, phi tilde. So it's just a, you get that it's a holomorphic function on CP1. But you know that on any compact Riemann surface, yeah, any holomorphic function is a constant. Yeah, so phi tilde is constant. Yes, so this was the solution that was assumed. Ну, не, ну это не совсем очевидно. Ну, это несложно проверить. То есть, ну, как, ну я говорю, how to formally check that it's holomorphic. Yeah, check locally, yes. Yeah. So, yeah, of course, you're right that what we indeed. So indeed, we choose any point. So we want to check that it's holomorphic. Yeah. So we choose any point here. I don't know, x. So it maps to C over gamma, and then here, okay, here then you have phi over x. And then okay, and then you choose a coordinate chart around it. So U. Then here you have C pi. Yeah, and then you choose here open set V such that I mean pi from V to U is an isomorphism. I mean, this is how we introduce coordinate charts on our torus. Yes, and yeah, but also I mean we choose such V such that that contains, because I mean here we can I mean of course we can choose many V's such that this is an isomorphism up to a shift by our lattice, but you choose V such that it contains phi tilde of x. Yes. Okay, and then you formally you okay, it's phi tilde. Oh, yeah, of course. Yes. No, yeah, sure. Yes, and then yes, and then you choose some small neighborhood here. So some I don't know v U tilde. So an open neighborhood of x, such that phi of U tilde is in U. Yeah. And then you just check, and then you just see that phi tilde restricted to this u tilde is just yeah, composition, this one. So it's just phi composition pi inverse. Yeah. Yeah. So because how you, of course, yeah, I mean you choose u tilde a small ball around x, so simply connected. So what you say? So how to check this property? I mean, you check it just again using this theorem, because this theorem says that there is unique map such that. And then, okay, if you look locally, then you see that I mean, this map. So how to say that? This is called the theorem about lifting map. Yeah. So you apply now this lifting map to u tilde, and see that this map lifts phi. And this map also lifts phi over u tilde. So we have this equality. But then this is clearly holomorphic, yeah, because it's a composition of holomorphic maps. So this is holomorphic. Yeah. Okay. Are there any questions? Okay, then we finish.